will continue with our second presentation, where we have the pleasure that we can give you an insight to my main research interest at the moment. It's actually the question of how to make circular economy a self-runner. And so we will present to you two projects, one big priority project, the SPP 2443, funded by the DFG, and the other, the collaborative big project of Decide for Eco, funded by the Federal Ministry of Energy and Economic Affairs, the BMWK. So we, that is Sven Rarbach and myself. I'm Gräßler and my academic roots are in Aachen University. There I completed my studies in mechanical engineering, my PhD, and then my habilitation, for which I received the venia legendi in engineering management. And now afterwards I spent 12 years at the Robert Bosch Company and several management functions all around product creation, and 12 years ago I came back, I returned to academia here at the Heinz Nixdorf Institute.
Thank you very much. My name is, and I've already said, Sven Rarbach. I'm on the chair of product creations in 3 years. I'm a research associate, and I started my academic journey in the project Impact, which is a project which we had a deeper look at model-based systems engineering and especially at model-based impact assessments for engineering changes. But now I'm the project manager for the project Decide for Eco, which Ms. Graessler already talked about. And there we try, or we're combining the two worlds of MBSE and especially of product lifecycle management with the domain of sustainability.
Where did I put the point? Ah, here. Here it is. Okay, thank you very much. Thank you very much, Sven Rarbach. I will show you the structure now. First, I will introduce you into treating circularity as a business opportunity. And then in the second part, I will show you the data-driven decision support for circular economy. And we will complete this view by paving the way by product lifecycle management, PLM systems, and the collaborative data spaces, which will be presented by Sven Rarbach. Well, our consumer behavior overexploits natural resources and pollutes the earth. A statistic of the Circularity Gap Report of this year says that 93% of all the materials that we use to manufacture products are just wasted. They are not recycled at all. So this equals 99 billion tons of material every single year. It's really I cannot really imagine that. And this linear economic model contradicts our planetary boundaries and the idea of sustainability. For this reason, the idea of circular economy was born. It demands that natural resources are recirculated and used once again. This way, limited natural resources become unlimited. That's the main idea about it. And this name, circular economy, was coined in the 1990s already by Pierce and Turner. Oh, I'm sorry about that. Thank you so much. And they stated that closing these material cycles does not only pay off ecologically, but also economically. And that's the main point about circular economy, to really have an economic growth but at the same time respecting nature and creating sustainability. So actually circular economy represents the vision of treating circularity as a business opportunity. To conserve natural resources and the environment, material cycles shall be closed at the highest possible level. So we want to recycle, if possible, whole products and not only shredder the material and reuse that again. The fewest resources are taken if we are able to refuse a new product or to rethink it or to reduce the use of material and energy. An example of refusal if a product is made redundant, or an example of rethinking is if we use shared economy. So for example, we do not have to own a car in order to use it regularly. And an example of reducing is to improve productivity, for example, and spending less energy or less material on the production. Once it comes to the decommissioning, the material is collected, sorted, and inspected, and then the decision is taken on which level the material can be recirculated. The highest possible level is if the product just changes hands, if it is just reused. For example, an old used car that I sell to Sven Rarbach maybe, and he uses it also as a car for himself. That would be an example for R3. R4 would be an example to repair if I sell my old car to a car handler, to a car dealer, thank you. And then he makes a check-up and he repairs one or the other thing and then he resells it. If the product value is enhanced, we talk about refurbishment, and lower levels of recirculating are remanufacturing, repurposing, or at least recycling the shredded material or recovering the energy. So we have a common VGAP and VGP. VGAP is the scientific community of product engineering, and VGP is the scientific community of production engineering. And they stated in a position paper that we need so-called update factories, where old used products are brought to a current technological standard in an industrial manner, like a software update, but in this case, an update of the whole functionality, the whole physical product. And this would extend the useful lifetime of a product and thus contribute to saving energy and material. Okay, in order to achieve this material circularity, we need, of course, information circularity. To decide how I can reuse the material, whether I can reuse the whole product or only parts of it, or even only the material in itself, I need to know which loads the product had to bear, what was the usage profile, how is the maintenance and the repair history. And from this I can imagine how to make further use of the product. So let's come to the data-driven decision support for circular economy. To gain deeper insights, we have to cope with extreme data. Extreme data has many phases. It can be just complexity, diverse data sets, multilingualism, increasing volume, like the term big data says, increasing speed, uncertainty, and also scattered data sources. And so extreme data is, we understand it as data that has one or more of these characteristics to an extent that make current technologies fail. This definition was coined by the European Commission in the research funding call Horizon Europe. And together with data sciences and artificial intelligence, the extreme data harbors a big potential for gaining deeper insights and thus accelerating decisions in product creation. However, in engineering sciences, the challenge lies in integrating extreme data into our well-proven and established engineering methods, such as heuristics, methods, modeling, product modeling, simulation of behavior. And our world, in an analog way, we had only very few data, very little data. And to be able to assess the system properties or the system behavior, we had to find out what are the cause-effect relations. We had to put them into physical formulas and calculate them. So this was a long way that took a lot of time. But the engineer who made this calculation, he or she is able to take the full responsibility for such decisions because he and she knows why it works this way and no other way. We talk about causalities. And a precondition for working with these causalities is that we qualify the data along the knowledge pyramid and aggregate the data. Now, with the extreme data that we have, we can accelerate that. We can reach our destination much faster because in addition to our causalities, we add correlations. And this is much faster and sometimes even more precise. Also, extreme data can be used immediately and is more and more available along the whole product life cycle. So actually this will change our way of thinking and of decision making, and for the engineer who is trained to trust and to rely on causalities, he or she is not yet able to take over the personal responsibility for such a mixed decision situation. And therefore, we have to find new ways of, we call it hybrid decision support. And this is what we do actually in our priority program SPP 2443. We strive to increase the efficiency of product creation through this hybrid decision support. We started also half a year ago, and we have 6 different individual products from 11 universities, and we have a focus on gearing product engineering with production engineering. So this is very important and a fascinating interface. And well, we just started our work and we'll look at very different questions along that interface. We will make a scientific symposium in March next year where we collect all the different articles and papers for this hybrid decision support, and you are cordially invited to reach in your paper. But let's now look at the boundaries, the product lifecycle management and the collaborative data spaces.
Building upon the information, the challenges, and the potentials of decision-making in product engineering, I'm just going to give a quick overview of what product lifecycle management tools can do for us in product engineering and how we can use collaborative data spaces to advance those functionalities, and especially advance those functionalities to assess sustainability in the engineering process. But starting with just the core of product engineering, decision making, when we are talking about decisions in the product engineering process, we need to consider different types of data. We have a lot of data silos and system and all that kind of stuff in which data is that we need to use for valid decisions. And most of the times when people talk about decision making, especially in the world of engineering, it's a statement about 70% of the costs are determined in the early phases of engineering, or especially nowadays with the trend of sustainability, that a huge amount of sustainability or environmental impacts are determined in the early phases of engineering. We need to advance the decision making and implement more data through the product lifecycle management. But when we're just looking at sustainability is a new dimension in product engineering. We just can't add another layer to our normal product engineering process. We need to look at all the disciplines. All the design principles need to be advanced to have a look or to implement sustainability in a holistic way. We can't just take sustainability, assess it, and make a retrospective life cycle assessment to call it sustainable. We need to really get into it and advance product life cycle management so that we are able to advance the decision making in the early phases of the product engineering, and are also capable of making the proof of compliance regarding some environmental impacts. This is why we need to look at further informations and data in the data silos I already talked about. We need to implement, for example, material data regarding the recycling rate or the sustainability and add those up in our decisions. We can't just look at the resources in the material data. We need to take a deeper look at the use phase of the data. Can we recycle it really? What are the environmental impacts? Like how many tons does a specific plastic emit when we use it, when we build it, when we process it? And this is why we need a new layer or a new functionality in our established product lifecycle management. And especially we need to look at the sustainability as a moving target. So we can't just look at it like a boundary condition which is fixed where we can develop. So we have a fixed point and can say we have a requirement, the driver needs to be a specific dimension. We really have to look at a moving target because the regulatory conditions in which we need to engineer those products, they change. Nowadays, we talk about EU regulations regarding the eco-design. Nowadays, there are some information we know about, but we are not really sure what is in there and how can we implement them. And so the methods we are developing or we choosing in our product lifecycle management need to be flexible so that in the end, the engineers really get an advantage of using those tools, that they can choose for which value they're going to optimize, and in the end, to have a holistic approach in which sustainability assessment really makes an advantage for the engineer. Current product lifecycle management tools most of the times give a structure for data like bill of materials, CHD models, and product-related information. Also like requirements, functions, and sometimes logical elements. But when we want to talk about sustainability at itself and a holistic vision on sustainability assessment, we need to implement other types of data. We also need to look at real-time data to get a better understanding of the production process of the product itself so that we can emphasize or especially look at the real sustainability, the real environmental impacts a product will emit. And in the end, we need information from the whole value creation network. We can't just look at our organization itself. When we're talking about modern products, there are always included some suppliers, some stakeholders, where we need data from to make a real sustainability assessment. And this is why we need collaborative data spaces. Here an example of the Manufacturing X data space. There are other kinds of data spaces advancing right now, but the technology itself is not ready yet. It's not implemented in a huge amount, and this is why in our research project we built an initial demonstrator to get a better feeling for the data space itself. This is our initial demonstrator to visualize the secure exchange of data with the data space itself. To exchange that information, we need a special kind of connector to make sure that the information are exchanged in a safe way, that they are only accessible by the person which had the real contract, and in the end, that only data belongs to the person which provided it to the data room itself. Therefore, we have the EDC connector. It's the Eclipse Data Space Component Connector, which is the software component which enables us to make a secure and reliable data exchange between different partners. We implemented this to access the data room, and in our example, the site for Echo, or in a broader scope, the manufacturing X data room. And in a simplified way, we have two stages of the EDC. First of all, the control plane, where all the contracting happens, and the other plane, the data plane, where in the end the data can be exchanged. Each part of the, or each organization in the data space needs an EDC connector to connect to the data space itself, and is then able to exchange data to another. In this example, we are in the bottom, and HardiePlast, a supplier of plastic parts, wants information from our laboratory. And so first of all, we need to make a contract about the control plane, so that in the end, HardiePlast is able to get access over the data plane and really get the data from our system themselves. And the data are structured in the form of the LSAT administration shell. So most of you should or could know this from the industry platform 4.0. This is a data format which is standardized and which holds a lot of information regarding engineering, but in other domains it's already into. And we use those data formats so that the other organization is capable of interpreting this information. In our current example, we're using the product carbon footprint submodel, which we then can share with other parties of our data space, and they can interpret the values which are in this data format. This is a storyline in which, for example, HardiePlast can access the product carbon footprint for a product which is manufactured in our smart laboratory. The smart laboratory in the example is, or gives us the possibility to give all the kinds of data to the data room in which we are in. So we can build up data in our smart laboratory behind you in different forms, so that we can build sustainability assessment in different ways. When we're looking at sustainability assessment in the early phases of product engineering, most of the time it's only the calculation of some product features like the volume with some kind of environmental impact through a life cycle inventory database. But when you want to make better decisions or decisions with a higher quality, we need to implement primary data from machines like the machines in our smart automation laboratory and calculate them with the other factors to get real environmental impacts. And we use our laboratory in the data space itself to give the other partners the opportunity to make assessment in their own system and to provide different forms of data for them. And in our own laboratory, we have a first prototype to make real decisions or make real assessments of sustainability regarding a huge amount of environmental impact. And this is visualized here in a prototypic dashboard where you can choose the life cycle impact assessment, so the basis for the assessment of the environmental impact, and make flexible assessments for your product itself. So engineers are capable to calculate environmental impacts via the data model, which is filled or which is exchanged by data from the data space, and the engineer itself is then capable of choosing the grounding or the base for the calculation and can take real decisions in certain decisions point. For example, in this screenshot, the engineer is capable of choosing a solution alternative for a gripper solution. And he wants to calculate the environmental impact by the life cycle impact assessment method by the ISO 15804, and he wants it in the format of climate change. The engineer can then choose a solution for the gripper depending on the environmental impact. In this case, he can look at the different quantities of the CO2 emission for the different alternatives. We developed other features for product lifecycle management and for the sustainability assessment, and broadened the scope and implemented them with our IT partners from our project in already established tools. The established tools are, for example, the product lifecycle management tool from Siemens Teamcenter, where we implemented some functions regarding the sustainability assessment. The data came from the data space by the connector, by the EDC connector, and we were now able to implement different kind of metrics in the system itself through our features that we developed. This means that we are able to implement metrics like land use, water use, and other environmental impacts in the system itself, so that the engineers can use those informations for better decisions or for more sustainable decisions. We also add features for the assessment of data quality, so that the engineer itself is really capable of interpreting the value, so that he just don't get one value which he can then use to make a decision. He's also capable of interpreting the value for himself. In this case, it's a 5-stage data quality, and at the lowest tiers we just have secondary data from lifecycle inventories, and at the highest stage we have primary data from their own machinery. But the engineer is then capable of interpreting the value and can make better decisions regarding the value which is on the land use. And in specific decision points, he can then compare different versions of the product and has a real calculation to build up on his decision and develop more sustainable products. And our main goal in the research project Decide for Eco is to build method and tools for the model-based and predictive as well as flexible decision support in developing ecological and circular creation. In the end, we are in the Manufacturing X Cosmos, the sustainability-based project where we try to advancing the PLM functionalities to really get the sustainability assessment in those tools and to help engineers make better decisions regarding the sustainability, and in the end contributing to the sustainability future through data spaces in product engineering.
Thank you very much. And last but not least, we will invite you to reach in your paper to the HIPPE symposium, where all these fields of knowledge can be discussed and can be presented. We will perform it on the 25th to the 26th of March next year, and you can reach in your paper until the end of August. So we would be very happy if we could take this as an opportunity also from the other chairs here at the HNI for a deeper collaboration to these very vibrant topics. Thank you very much so far, and now we are of course happy to answer your questions.